Let's do this. Let's go with topic 12 first. Let's start with topic 12. And then let's go ahead and do this revision for topic 12. Oh goodness. Oh no, I accidentally saved it over. So all my notes have all those drawings. Shit. Okay. Hang on, let me just get a clean copy of it. Ouch. Ouch, 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 ouch. What a zoom sometimes the pictures. Wait, yes, Mingler, you're letting me speak, why? Why? What's going on? Hang on, I need to. Where's the PDF? PDF. Hang on. Okay, so this is topic 12, huh? Are people even going to go to school now this week? But Friday is the last day of school, eh? Okay. Um, what's this all about? This chapter? we're gonna just revise photoelectric effect today, and then after that we just go into paper, right? Because photoelectric effect is quite heavy on its own, but maybe I don't know, maybe it can be quite fast. I don't know. Yeah, perhaps it can be quite fast, right? What's going on here? Photoelectric effect. What are we trying to do? So we're trying to prove that light is a particle, so light exists as photon, right? Okay, so what's the action? What's the setup of proving that? What do we do? We shine? Yeah, we shine monochromatic light. So this experiment here, topic 12, photoelectric effect, we shine monochromatic light. We shine color specific light. That means we select a color, we select a certain color, and we shine only that color, right? Onto what? Okay, metal plate, right? Not a gas, not a cloud or anything like that. Metal plate. Okay, what we trying to do? What we trying to do when we try to shine the light on that metal plate? Like what's the purpose of doing so like that? You know, you have a metal plate, okay, like that, and you're trying to shine light on it. Okay, you're trying to shine light. What's the purpose of shining the light on it? So we want the electrons to come out. Whose electrons? The metal plate's electrons, right? So the electrons on the metal plate, right? There are electrons on it, and we are trying to shine the light on the electrons so that the electrons can absorb the energy and then jump out. Correct? Yeah. So that's the thing. So what's the requirement here? What's the requirement here? That means the photon, right? The photon must have what? What must a photon have? This is your photon, right? So what does your photon must have? Then what? Yeah. So in the simplest form, right? We understand that the metal has a certain work function, right? We understand that it has a certain amount of work function. Work function meaning what? Now it sounds like a very complicated term, but work function is simply the energy required to emit the electron. Work function is the energy required by the electron to be emitted. So this photon here, right, must have minimum energy equals to work function, right? Work function, right? So the photon must have minimum energy equals to work function. How is this different from the discrete energy levels? How is it different from the discrete energy levels? Discrete energy levels is what? The photon must match the same difference in the energy levels, right? Correct or not? Must match the transition, right? This one here, no. This one here is just you must have the minimum energy, right? If you're more than the minimum energy, the electron can absorb also. So it's not like the light will pass through unabsorbed. This is a different case, right? This is a different case from like discrete energy levels. So this one here, as long as you minimum, right? Once a photon meets the minimum, right? Any other energy the electron can absorb already, right? It's not like the electron will not choose to absorb. Okay, now I know it sounds a bit strange, right? Why do they behave like that? Why do they behave differently? Because in the discrete energy level, the gas cloud, right? The atoms will only absorb certain fixed amount of photon energy, right? But then yet for this one here is as long as you hit minimum, it will absorb any photon of more than or equal to the minimum energy, right? But it's just like that. It's a different case. Why? Because this is a metal plate. It's a solid metal. This is not like the gas. Understand this? So once a photon is absorbed, right? Once a photon is absorbed, if this photon has more energy than the work function, what will happen to the electron? The electron will escape, right? The electron will escape or be emitted, and then the electron will have Ke. Okay, will have Ke. So your understanding is the photon gives the electron the energy for it to escape. For it to escape, what must it minimally have to overcome the work function, right? Then whatever surplus, whatever is in excess, then it will come out as Ke. So do we understand that the photon energy, right, the energy of the photon is basically equals to the energy of the work function, okay, right, plus the Ke of the electron when it's emitted, like that. I mean, that's the energy accounting, right? That's the energy balance. Okay, that's the energy balance. If you have, if your photon has not enough energy even to meet the work function, then there's no talk about the Ke, right? So the Ke is like whatever surplus. If you just nice meet the work function only, then you have no Ke coming out. Okay, so far? Can All right, good. So now we have to go into a little bit of small details. So the photon's energy is dependent on what? What's the equation for the photon's energy? Right. So the photon's energy is hf, right? So frequency refers to the color. So there must be a minimum frequency, there must be a minimum color, right, in order to emit the photon, the electron, sorry, to emit the electron. So this hf, right, tells you the total energy of the photon. What's another equation that you could use, they could make you use instead of hf? Instead of hf, what could it make you use for the energy of a photon? hc over lambda, right? You could either use hf or hc over lambda. But then when you talk about hc over lambda, right, what do you understand about the lambda? The lambda must be a maximum value, right? You cannot have anything more than that wavelength. It's the reverse of minimum frequency. But they rarely ask this question, right? They rarely ask this question. Not that they don't, but they rarely ask this question. But our understanding is that the wavelength cannot be more than a certain amount. Okay, work function then. What's the equation for work function? What's the equation for work function? Well, technically, work function should be just a value itself, because that should be just the amount of energy that the metal plate right needs. Sorry, the electron needs to escape the metal plate, right? But we can write it as hf naught, right? Which indicates that that's the minimum frequency that you need for the photon, for the electron to escape, right? Again, whatever surplus, you get your Ke, right, of your electrons. So right here, right now, the first relationship, very quickly we established already what's the first relationship. The frequency of the incoming light will affect the amount of Ke that your electron has. Okay? There is one small thing that I think I didn't address when I was teaching this class, like way back then, right? And that was this. There's this idea of Ke max. There's actually a word there at the bottom here, right? Ke max. You can see, right? You can see it, me typing in the notes as well as inside the notes. I never really addressed this Ke max, but now I address it, right? But if I did, then okay, but now I'm just repeating it. Why is there this idea of Ke max? Okay, so let's zoom in onto the plate itself a bit, right? So I'm gonna zoom in a bit. So if I zoom in, right, you will see the metal plate kind of like this, right? Some electrons are right on the surface, some electrons are slightly further behind, some electrons are, basically the surface electrons have different positions, but there will be just some that are right on the surface of the surface on the metal plate. Okay, when the incoming light comes, is shining on the plate, right? When the incoming light shines on the plate, the photon, right? The photon comes in, and the electron absorbs the photon. When the electron absorbs the photon, okay, you realize that some of them are embedded further inside, some of them are slightly further outside. Okay, so when you take HF minus HF naught, right? When you take HF and minus HF naught, right, and then you get Ke. This Ke, right, is actually the Ke of the most loosely bound electron. Ke max of the most loosely bound electron. Okay, most loosely bound electron. That means this is the electron that happened to be way out at the surface and is readily easily going to be emitted out already, right? So if he's the most loose one and he gets emitted out, right, he will have that term Ke max, right? You understand this? Of course, then the question will be like, oh, then how about those that are further behind? Like, do we need to care about their Ke? The answer is no. You don't have to care about their Ke. You don't have to care about the Ke, right, of the other electrons, because we are concerned about the one that is most easily, right, like lost out of the metal plate. So we are concerned about this one here. So therefore, when you do calculate HF minus HF naught, the work function is meant, right, for your calculation based on the most loosely bound electron to the metal surface. Okay, different electrons will take different paths to be emitted. Therefore, right, they will have different kinetic energies when they come out. The one with the maximum Ke is the most loosely bound electron, right? That's the phrasing. Are we okay on this so far? Yeah, right. That's the phrasing. Okay. So therefore there's this concept of Ke max. All right. So one more time again, right? Frequency of the light, the color of the light. Violet has the highest frequency amongst the visible light. UV even higher, X-ray even higher, gamma rays even higher, right? So whichever photon you use, the higher the frequency, the greater the Ke max electron, right? The electron with the highest kinetic energy. Take note that the light does not change the work function. The work function belongs to the type of metal that you use. So for the same type of metal, change. Okay, right? So work function is constant for a certain metal. Okay, right? So for a certain metal, work function is always constant. It does not change. Do we understand this so far? Okay, can right. Why? Because over the weekend, I've had some students who ask me questions like, they just see all the physics equations as though they're math equations, which is quite unnerving, right? Because they tell me this, oh, if I increase the energy of the photon, then wouldn't the work function increase? Because they just see it simply like a math function, like A equals to B plus C. If A increase, that means B and C will increase, right? Like, so the question is, I challenge back at the student, right? So I want you to consider this equation, and just to sidetrack a bit, just to make sure that you understand the difference between physics and math is that physics, you need to understand, you need to make sense of what the variable is. Like for example, F net equals what? F net equals to MA, right? If let's say I want you to calculate M, how would you calculate M? M will be F net over A, right? So if I increase the resultant force, let's say I add more force acting on it, does this mean that the mass of the object will increase? Right? That's the problem. Some students don't care about what the variables or the letters actually mean. They just see it as a math formula. Oh, F net increase means M must increase also. That doesn't make sense. You apply a force, how can the mass of the object increase? So that's the thing. You need to know exactly what changes, what doesn't change. Like, so for example, for this one here, if you add in more if you use higher energy photons, does the work function change? No, it doesn't, because it depends on the metal. So you don't just see it as an equation, you see it like, how it makes sense in the setup. So HF naught is the work function of the metal here, right? Whereas this Ke max will be the Ke of the electron that's being emitted out. Are we okay on this so far? Can I? Right. So therefore, right, we need to also find out, because so recently we have encountered some questions like your school prelims also, right? The ACSI prelims, the MCQ. There was one question about intensity of a wave, right? That was quite frustrating, right? That part there, right? So we have to address that one here. But just to make sure that you understand this, so on this page here, frequency affects what? Ke, and Ke affects stopping voltage. Okay. So here's the next thing. We now know, and I think everyone agrees, right? Because I've repeated it so many times today already, right? That you know that the Ke, right, refers to the Ke of the electron. Correct? Okay. But how do you measure the Ke of the electron? How do you know how much it has? How do you know how much Ke this electron has? Are you going to put a speed meter there? Are you going to measure? How do you measure the Ke of an electron, guys? No. How do you measure how fast the electron is? You know what's the first fundamental problem? Can you even see the electron? You can't. So how do you know how much Ke it has? How do you measure the amount of Ke that it has? Is there a Ke meter? No. So what should you do? What can you do? Think about, like, this. I mean, I'm going to give you an answer in about 20 seconds. Right? Think about it. How do you measure the Ke of the electron? Because you need to measure it. Right? No, current cannot, because current is in the wire. So you cannot use an ammeter or anything. You understand that? So in order to measure the Ke of an electron, which you can't even see in the first place, is you put a plate here, sorry, you put another plate here, right, with a negative voltage. Right? You try to do what? What do you try to do? You try to prevent the electron from touching the metal plate. Then yes, you connect an ammeter to this plate, right? You connect an ammeter to this plate, and you make sure that the ammeter reading is 0. You make sure the ammeter reading is 0. Okay? By setting it up like this with a metal plate that is negatively charged and has a current of 0, you are able to find out what is the Ke of the electron. But how does that work? How does putting a plate here and making sure the ammeter here with a 0 reading and a 0 ampere reading, how does that make, like, how does it help you calculate the amount of Ke that it has? Because of potential energy, right? This is basically topic 10. Topic 10, electric potential energy. If this electron has Ke and it flies over and you're trying to repel it and it stops here, what is the Ke here? How much is the Ke here? When it stops, it's 0, right? 0 volts, right? Okay, where did the Ke go? What did it become? It became EPE, right? It became EPE. So this Ke here has become EPE, right? Ke has been converted into EPE. Okay? I mean, we know the mass of the electrons from the data booklet, but what's the speed? There's no way for you to measure the speed directly. So what we do is we measure the amount of EPE. But how do you measure the amount of EPE? Is there such a thing as an EPE meter? Is there such a thing as an EPE meter? Don't have, right? No such thing as an EPE meter. So how do you measure EPE then? Yeah, so the charge of the electron, right, multiplied by the voltage of the plate, which is going to be a negative volt, so because we're trying to repel it. But that's the voltage here, right? We call that the stopping voltage. Okay. Now, are we able to adjust the voltage of the plate? Are you able to adjust the voltage of this plate? You are, right? Okay. So in order to prevent the electrons from touching this plate, you can adjust this plate to be negatively charged. You can adjust it to have a negative voltage. But you adjust it such that the moment the current just became 0. right? Then that will be the stopping voltage. Let's say, for example, guys, let's say, for example, the stopping voltage here, right? Just example, inside this example here is negative 4.5 volts, right? Okay, just an example, okay? That means you need 4.5 volts of negative voltage of this plate to stop the electron. What happens if I adjust this plate to 4.4, negative 4.4? Is it negative enough? Not negative enough, right? How do you know? How would you know that it's not negative enough? The ammeter will give you a reading. Why? Because the electrons will be able to touch the plate, right? Once the electron touch the plate, the ammeter will give you a reading already, right? So negative 4.4 won't be enough. How about negative 4.7? Let's say I adjust it to negative 4.7. What will be the reading of the ammeter? It will be 0. But then, so does it mean that 4.7 is stopping voltage? No. 4.5 is the voltage just when the ammeter gives you a 0 reading. That's the stopping voltage. That means you increase from 0, you start to decrease from 0, you start negative 1 volt, negative 2 volts, negative 3 volts, right? You adjust the voltage until the ammeter just nice reaches 0 amperes. That's your stopping voltage. Then you use that to go and work out into this equation, right? The Q times V, right? The Q times V, right? Right? The charge of electron times the stopping voltage. That's how you work out what's the KE of the electron. Otherwise, there will never be a machine ever that can help you find the KE of this electron. You will never be able to measure it. You can only work backwards to calculate it out. We use voltage. We use the plate's voltage to help us work backwards to find this KE. Okay? All right. So to tie up the whole first relationship, you increase the frequency, this photoelectron will have more KE. In order to stop the even higher KE photoelectron, you need to make the stopping voltage even more negative. Right? So therefore, on my notes here, right, I told you the relationship between frequency, KE, and Vs summarized at the bottom here. Right? Summarized at the bottom here. So this one here. Right? The higher the frequency of the incident light, the higher of the KE max of the photoelectrons, and therefore the larger the stopping voltage required. Right? And even then also, we have an equation that links the two, which is written here. Half mv max squared is equal to EVS. Right? E being the charge of electron times Vs the stopping voltage. Right? So if you want to put down an equation, then you should be able to write this down. HF equals to HF naught plus KE max, right? KE max, correct or not? This equation correct? Okay, rewrite it. HF equals to HF naught plus EVS. You can change it to EVS if you want. Right? You can change it to EVS if you want. Right? So that means that if I can simply ask you, oh, I give you this photon energy. I tell you that the work function is this much, and I ask you, predict what will be the stopping voltage. Can you find the stopping voltage? Yes, you can. You will be able to find the stopping voltage. Yeah. Right? I will give you an example now. Like right here, right now. Okay? So I give you an example. I have a photoelectric cell setup. Okay? One plate, another plate, emitter reading is 0. Can? Right? Incoming photon, right? The wavelength is 400 nanometers. Right? 400 nanometers. The lambda naught of this plate is 450 nanometers. Okay? Find the stopping potential of this plate. Right? Right? Find Vs. Like that. I just give you two values only. This one, this one. That's all. You can figure it out. Okay, hang on. I need to check on two of them outside because tomorrow they got the end of year exams. So I'll be back in 2 minutes. Where's my voice going on? Okay, now what's the stopping potential? Say what? 0.35 volts. Oh, okay, that's all. Cheap. Okay, so this is negative 0.35 volts. Okay, yes, negative 0.35 volts. Can make sense, right? Okay, so what would this look like on a graph? Anyone who's unsure about this, like oh, how do you get the stopping potential to be negative 0.35? Everyone's okay, right? Okay, okay. How would the graph look like for this one? Let's say I ask you to draw the graph. Like what graph though? What's this graph? What graph am I drawing? I know there's a photoelectric graph, there's a quantum graph. What graph is it? What axis and what? Yeah. Ah. X is voltage, right? Voltage of this plate. The voltage of the collector plate. Right? And then the y-axis, what's the y-axis? What's the y-axis? The current recorded by the ammeter. The current recorded by the ammeter, yeah, correct. That's the current recorded by ammeter. So I'm gonna ask you this, okay? What if the collector plate, right? The x-axis, the voltage, so this is V of collector plate, right? Because you all don't usually write the whole thing down, so that's why it's hard to remember. What if the voltage, right, is negative 0.35? That means I put here negative 0.35 volts, negative 0.35 volts here like this. Like where's the point on the, I mean the point of the data is just here, is just here. Right? Okay, what happens if I make the collector plate, right? I make it negative 0.4. I make, what happens if I make this plate negative 0.4? Negative 0.4 volts. How does graph look like? It's still zero, right? So that means if I make it negative 0.4, then the graph will go backwards like this, still zero. Like no matter how much more, like if the more negative you make it, the more likely you're not going to get electrons coming back, right? Touching the plate, right? So therefore the graph will just be zero all the way here. There's no current recorded at all. So what happens when I make it less? What happens if I adjust this voltage to be less than negative 0.35? Let's say negative 0.28, for example. Then what will happen to this graph? The graph will start rising, right? Okay, so the graph will start rising, and you know the general shape looks like this. Right, that's the shape of the graph. Right or not? Yeah? Yeah? Yes? Yes? Huh? Oh, then you should ask why. Oh, you know why? Oh, no, yeah, it's correct. I mean, that's what it is, lah. Right? Usually, by the time the collector plate is about like 0 volts, you would already reach the maximum current already. Okay? So I'm gonna ask you this: how come it doesn't increase any further? Why don't it increase any further after this? Like, why does it plateau? Why does it reach this thing called a saturation current? How come, like why don't it get more? You see, I make the plate positive there, guys. On this side of the graph, right? The graph here, the plate is positive. Positive plate, positive plate. Doesn't it attract the electrons? Aren't the electrons attracted over? Like, I would attract the electrons, right? But how come even though my plate is positively charged here, these are all positive charges here, by the way, right? That means these are all positive here, right? These are all positive values here, right? These are all positive values. So why is it that that even though it's positive here, the current doesn't increase anymore? Depends on what? Depends on, yeah, I don't like the word though. I don't like it when you use the word intensity. I really don't like it. Why? Because it's a bad thing, that is a bad habit taught by your teachers. Yeah, they just tend to just say the word intensity. But what's it caused by? The rate of photons. The rate of photons is fixed, right? So the key phrase here is the rate of photons. Rate of photons, right, is limited. Rate of photons. So if the rate of photons is limited, then the rate of what is limited? The rate of electrons is limited, right? The rate of electrons is limited. And therefore, the current that's flowing inside the wire here is also limited. It's limited by the rate of electrons. Like, let's say you have like a million photons per second, right? And only about 10,000 photons, electrons, right, get emitted. Like you at most you will get only 10,000 electrons going in the wire. Like that's it. No matter how positive you make it, you're still going to only get 10,000 electrons per second only. Like you can't increase the rate of electrons if there's like a limit to it. Mm. Why? Because they don't want to overcomplicate it. So for me, right, I want you to be extra clear. I want you to be explicitly clear, right? So we don't use the word intensity, we use the word rate of photons. Okay? Right? So it's not ambiguous at all. Right? I would really have hoped that the exam questions were a bit more clear on this as well. But yes, they are also a bit unclear on this. They use the word intensity, right? But it's a very loosely used term. Unless they say something like this: intensity of a particular color or intensity of a particular wavelength, then that's also quite clear. Because you're not changing the color, you're not changing the wavelength, but you're changing the intensity. How do you do that? You do that by increasing the rate of photons. So if you want to be extra clear, you say the rate of photons of a particular wavelength, or the rate of photons of a particular frequency, or the rate of photons of a particular color. You understand this? Okay. Question: how can I change the stopping potential? Right here, right now, the stopping potential is 0.35. How do I change the stopping potential? What can I do to change the stopping potential? What? Change the light. Right? I can use a different wavelength. What happens if I decide to use, let's say for example, I decide to use a bit like UV. Let's say I go with like 200 nanometers of wavelength. 200 nanometers. How would it appear on the graph? Without drawing, how would it appear on the graph? Right? It will be, right, the stopping potential will be more negative. Right? The stopping potential here, like Vs of 200 nanometer light. Right? That will be the stopping potential of the 200 nanometer light. Are we clear on this? Can right? So the color of the light, the frequency of the light, what does it affect? It affects your stopping potential. All right. That means I change the light. Okay, Anis? Well, basically, you already been introduced this, in the last couple of lessons. I already did mention already. So for intensity, right? For intensity, I want you all to remember is again one more time N over T HF over A, right? I'll tell you this, okay? I make you all memorize this, right? You can go to school, right? And you can ask around, right? Some people will not even realize that intensity for quantum is based on this equation, right? They'll just think that intensity is just number of photons only, right? Okay, so please take note that there are two factors to it: rate of photons and the frequency of each photon, right? The energy of each photon. Are we clear on this? Can Okay. So once you have, so you see, right? You see my statement here. I hope this is explicitly clear. The higher the intensity of a particular monochromatic light, that means of a particular color, right? Particular monochromatic light means frequency, right, is constant, right? That means you use the same monochromatic light, but the intensity will be the rate of photons, right? Then I understand. Then this is very, very clear. Okay, right? The clearer you are in your answer, the better, right? So higher rate of photons, right? Higher rate of emission of photoelectrons, right? And higher the current in the circuit like this. Okay. So saturation current is when you hit the limit of the rate of photons. or the rate of electrons. Okay, so saturation current is when you have the maximum, right, rate of electrons emitted, right? That's your saturation current, maximum rate, right? Rate of electrons emitted. That's for your, right, saturation current. Yeah, how do you change the max rate of electrons? Work backwards. You need what? More what? You need more what? You need more photons per unit time. You need a higher rate of photons. But am I changing the color of it? I'm not changing, right? So I increase the rate of photons. Yeah. Yeah, I understand. When you increase the rate of photons, means that you're increasing the intensity. I get it, right? I get that. But I want you to be explicitly clear. I want you to understand that when I say changing the rate of photons, I'm saying changing the rate of photons of a certain color. Yeah, right, of a certain color. So when you read the question, okay lah, I mean, to be honest, you have to read it very carefully. What if I tell you this, okay? How about, like, two different colors, but of the same intensity? Let's say I have blue light and I have violet light, but they have the same intensity. Let's say I want you to compare between blue light and violet light of the same intensity. Like, how do they compare? What does it mean then? Blue light and violet light of the same intensity. Let's say you have a question, blue and violet light, right, of same intensity. What does that mean? Blue and violet light of the same intensity. What does that mean? What? Lesser, right? Okay. So for the same rate for the same intensity, blue light, which has lesser amount of energy per photon, right, will have more photons per unit time. That means the rate of photons is higher. Violet, right? Violet will be, this purple doesn't look purple. Okay, violet will have higher energy photons like that. Like this is a HF of one violet. This is the energy of one violet photon. Right? And the blue one, this one will be like the HF of one blue photon. Yeah, I know, but I'm just asking you, like, I want you to compare blue and violet light of the same intensity. What does that mean? Say it. Yeah. Because, yeah, right? Yeah. Because you're thinking of the equation now, right? Yeah. But you see, a lot of teachers don't bother going there. They don't bother going there. Why? Because when it becomes too difficult, they don't want to explain it to you. They just leave it to you to figure it out. Right? I'm very sure no one bothered to go into this kind of detail, telling you that, oh, this is what happens when you have, right, blue and violet light of the same intensity. Very few people bother going through this because they know that it's hard to explain this. Most of the teachers will be like, you just hope it doesn't come out lah. Then afterwards just move on already. Okay? So there you go. So this will be blue and violet light of the same intensity. The caveat is I want it to be of the same intensity. Right? So then of course then the question is this: what happens if you use this kind of like this kind of light and you shine it on that metal plate? Let's say you go with the metal plate again, right? This metal plate again, and then you shine it with violet light and you shine it with blue light as well, right? I mean separately on separate occasions, and then you draw the graph. How would your graph look like? How would the two different graphs look like then? So again, don't forget they are the same intensity, yeah. Right. So how does the IV graph of the blue and the violet look like? So blue will be what? Tell me how to draw the blue one. Blue one will have, I mean, where do I start from? Where do I start drawing the blue from? Hey, why don't you draw it for me? You draw first, then I come and check your answer. Right, give me 2 minutes again. Let me check on the guys outside. Right, draw the graph, right, for blue and violet. Right, the ID graph. Okay, come. How does the graph look like then? I hope it looks like this. Okay, so your blue light, which is of a lower frequency than the violet light. Okay, so the stopping potential for blue will be less, and therefore your graph will look like this. Correct? Right, if I extend it out like that, so that will be for the blue light. Okay, but for violet of the same intensity, right, of the same of higher frequency, do you need it at home? You got one? Okay. Right. So for the violet light of the same intensity, then you will have, right, a graph that looks like this. A violet light would require a more negative stopping potential, and therefore the graph will start from here. But the one thing is, if you're using the same intensity, blue and violet, right, blue having a lower frequency but higher rate of photons, violet will have a lesser rate of photons, right? Lesser rate of photons means that the graph here will start from here and then it will taper off like that, right? So this is the violet. Are we clear on this? Right? Do you understand why now? Are you more clear on why? Yeah? N is number of what? Photons, yeah. So we started off with this equation. Okay, so this equation, let me just describe to you first. What does I stand for? Intensity. Don't confuse this with what I inside here. Current, don't confuse the current. It's not current, it's intensity, okay? Intensity by default is defined as power over area, watts per meter square, correct? Power. Power of my photons, power of my light, right? Depends on what? Depends on the energy of each photon, which is what? HF. Energy of each photon is HF, okay? HF here. And then N over T will be the rate of photons, because power is what? Energy over time, right? So what's the total amount of energy that you have? The total amount of energy will be the number of photons, right, multiplied by the energy of each photon. Then if you divide it by time, that's the power of the photons. That's the power of the light, right? So that's why that's the part that you can't get past. Okay. So what's the key phrase here? What did I say again? Blue and violet of the same intensity. That means they have the same I, right? Okay, they have the same I. But look at the equation again. If you have the same I, comparing blue and violet, who has more energy per photon? Violet has more energy per photon, right? So automatically, if HF is bigger, what will happen to the N over T? So therefore, we know that the violet has less rate per photons, right? Rate of photons like this, right? We know that, right? You know, like for example, I give this example here. For every 6 blue photons, as an example, we only get 3 violet photons for the same power, for the same energy. But it's only 1 photon each, right? So what's the deal between the electron and the photon? One electron can only absorb 1 photon. So it's either you absorb 1 blue photon or you absorb 1 violet photon, right? If you absorb the 1 violet photon, like what happens? Yeah, you get more Ke flying out, right? So it's harder to stop. Okay. But then if let's say you absorb 1 blue photon, your Ke isn't as much, but more electrons can absorb. So you get more photoelectrons. Okay? Right? And therefore you end up with this kind of graph here like this. Okay? And I think I mentioned in the class when I was running this before. I mean, what is your conclusion if you do see a graph that looks like this? Okay, let's say you look at the graph and you see the graph looking like this. Hang on, like that. What does this graph mean then? When you have two different colors, one is blue, one is violet. Again, violet has a higher frequency, so it's harder to stop. So the stopping potential is more negative, right? So blue, violet here. But then they end up having this same line here. What does this mean? Okay, I mean, you're not wrong, okay? But it just means the rate of photons is the same, right? The N over T is the same, right? For this graph here, the N over T is the same, right? The same for both. But you're right, okay? Because if you have the same N over T, then that means violet has a greater intensity, right? That's not wrong, okay? But I mean, the fact that the lines taper off like that together, right? That means that they have the same rate of photons. What if they don't say? They must say something lah. we have to read the question and try to figure out what they want, what they're trying to say, right? So I can't tell you like, you know, oh, if they say this or they don't say that, right? You just have to remember all these basics here. Don't anticipate what they can ask, right? Just remember all these basics first. Read the question already, then you realize, oh, okay, this is what they mean. Are we okay in this? Can right. Now, question though, have you seen this graph in your school's notes? This one, where the two lines join up in your school's notes. Do you remember seeing this in your school's notes? Don't know, you have never really looked at your school's notes before? Okay, all right then. Do you see this graph or do you see this one? You don't go school, but you're wearing school uniform? So your body is there, but your mind not there lah. Okay, I get it. Right. But anyway, yeah. So if you do see this one, make sure you know the difference between this graph and this graph here. Right? There's a big difference between the two. Okay. So well actually we are done with the basics here. Like this, we've gone all the way to the graphs here already. Right? That's pretty much it. I mean, for photoelectric effect, there's only two more things left. This graph as well as the relationships here. Right? But I think the relationships you already kind of sort of like, you know, I'll just tell you what the relationships are, right? There's a lot of words there, you're probably like glazing over already. Okay, but let's do this graph first. So this graph is what against what again? Let's say, I mean, you're revising, right? So let's say you're looking at blank slate, right? This graph is what? What against what? So what is the y-axis? Ke max. Ke max, okay? And then this one here, frequency of what? Of incident light, right? Frequency of incident light, okay? Incident light. Okay, hang on. Okay, you send me questions. If you still have, do you still have questions? Not now? Okay, can. All right, see you. All right, bye. Okay, so frequency of the incident light. Right. So this one here is like for any particular metal plate, right? For any particular metal plate, it will have a threshold frequency. It will have the F0, correct? Okay. And the idea here is this: as you increase the frequency of your incident light, what happens to the Ke max of the electron that it emits? It will just increase at that linearly. Okay, right, like this. Right, then you extrapolate it backwards. Right. Now, what's the equation of this line then? It's back to this one. HF equals to HF naught plus Ke max. Right? Ke max. But what are you plotting against? What against what? You're making Ke max a subject, right? Because this is the y-axis, this is y-axis. So Ke max is Ke max. So you make Ke max a subject first lah. Ke max equals to what? HF minus HF naught. Right now, if you rearrange it like that, don't you see that? Right, Ke max equals HF minus HF naught. But what are you plotting against? Hey, don't forget dotted line, dotted line. Right? But what are you plotting against? You're plotting what against what? You're plotting Ke max against F, which is the frequency of your frequency of your incident light. Okay, so do you understand what's happening here? Like, what are you doing to the experiment here? Like when you start increasing the frequency, like what are you doing literally? You're changing what? You're changing the color of the light, right? Let's say this F naught here is blue. Then you change here, this is indigo, this violet, this ultraviolet, this X-ray, this gamma rays. You know, like you're literally increasing the frequency of the light that you're using. But what's not changing here? You're not changing the plate. Am I trying to find stopping potential here? I'm technically I'm not lah, right? Technically I'm not. But here's the thing. Can I get you to agree that the y-axis is actually like stopping potential? Isn't the y-axis like proportional to stopping potential? Ke max is equals to what? Ke max is equals to what? Yeah, EVS, right? Ke max is equals to EVS. So that means the higher the energy of my electron, right, the stronger the stopping potential. So if I were to increase the frequency of the light, then the stopping potential gets harder and harder to stop. Okay? Now then we have to extrapolate this dotted line here, but why is it dotted here? Why is it dotted here? Why didn't I just draw a solid line? I mean, what difference does it make? Correct, because below the threshold frequency, below the minimum frequency, there are no electrons emitted here. So therefore, the data doesn't exist. Data will exist for all these points here along this solid line. Yes, the data here doesn't exist. I just extrapolate it to do what? To find what? What does this give me on the y-axis here? What? Negative what? Yeah, well, I mean, it's work function basically, right? It's the work function. So that's the HF naught, right? The value over there is the HF naught, right? The value here is the HF naught. That's the work function. Okay, so far? Okay, right? That will be the graph. Okay, that will be the graph. Okay, so that will be the graph. I hope you understand what's the difference between this graph and that graph, right? And you need to internalize it. You need to memorize it. This is like, I mean, if you join somewhere in March or April, okay, you need to get all this into your system because this is the last time I'm revising this already. There's no other time really. You all realize that you all only have 3 more weeks to go to the first paper. 3 more weeks only, you know, look at that. Like today is the 30th, right? 30th, today, 7, 14. That's it. That's it. 30th, 7, 14. That's it. Right? And then you got one exam. Right? And then on 29th is my last lesson with you. After today, you only left with 3 lessons, like 7, 14, and the one there. So that's the purpose of the tandem lessons because I'm covering as many papers as I can as well. Right? I'm trying to give you like 2 times the amount of time. Right? So like, you know, I hope you attended something on Saturday, Sunday, or you watched it at least, because the one that covered paper 1, right? Okay, I got some people asking me, you know, last night at like, you know, Sunday night, they asked me questions from that paper 1. I'm saying, dude, you didn't attend the tandem lesson, you didn't watch the video, is it, or what? You know, now you're asking me, right? Go and watch it. That's the whole purpose of that lesson, to go through questions, right? What? I wish paper 2. Or did I finish paper 2? I forgot. My pacing yesterday from Sunday is a bit slower. Yeah. Yeah, yesterday I reached paper 2, but I didn't finish paper 2 because of the crowd. Huh, what? Yeah, yeah, they got a lot more questions, you know? Okay, so it's fine. I'll answer the questions. All right, not leaving you in the ditch. But you have to tell me. All right, there you go. So then again, this Saturday and then the next Monday and then the next Saturday and then next Monday, you got enough time with me, right? Because here I am going through just the papers, right? But if you're still trying to like internalize all these things here, right? And you feel like oh, I want to internalize all these first before I start doing the practice. You are making a very very big mistake. If I will call out the names of those people who did that last year, every time telling me that they want to study first before they practice, right? Okay, I just go and find out who are the ones who got the 6. Those are the ones who tells me this all the time. They tell me they want to internalize everything first, right? Then they start doing the practice. But that's too late already, dudes. Do both. I mean, we haven't internalized it yet, then do both, right? Yeah. But those who have internalized it already, what's your benefit then? Your benefit is that you can spend the rest of the time on your other subjects, on Langlit, right? On, I don't know, geog, history, I don't know, chem, right? Chem, the grade boundary for chem is so freaking high, right? What else? Like Chinese also. Anyone retaking Chinese? Oh, retaking Chinese was like last week, is it? I don't know, man. Anyway, okay, so what are the last 3 things for photoelectric effect? What's the last 3 things you need to care about for photoelectric effect? Okay, you basically just have to prove why wave theory doesn't work, right? Sometimes, and why quantum theory helps us to explain the observations, right? What are the 3 observations? Minimum frequency, right? Frequency increase, Ke max increase, stopping potential increase, and then immediate emission. Okay, right? What's not considered as one of the observations, right? What's not considered as one of the observations? The 1-to-1 ratio. The 1 electron absorb 1 photon is not considered inside here, right? It's part of the theory. It's part of the imagination. Okay, I imagine that 1 electron only absorbs 1 photon, and therefore, if I imagine that, then it helps me to explain these things. Okay, and don't mix this up with discrete energy level. Yeah, it is not excitation or de-excitation. Don't use those words there. Right? If you write down your answer for photoelectric effect and you come and tell me things like, oh, when the electron excites or de-excites, well, I'm gonna lose it, man. Right? Because you obviously haven't compartmentalized your memories yet. Right? So don't don't. Okay, there you go. So you have all these things here, and then you have to state why the wave theory cannot. This one means like the wave theory doesn't explain this observation because wave theory says that we can accumulate the energy. All right. Then this one here is doesn't matter what frequency, what color it is, right? As long as the energy is strong enough, like intense red lasers. Then the last one here is this, right? I can accumulate energy, right? Then the electron can jump out. But then all these 3 doesn't explain these 3 observations. So then we imagine the quantum theory. Someone had to sit down and try to explain these things by coming up with the quantum theory. Okay? So your job for 3-mark question will be something like this, right? Explain why wave theory doesn't support the minimum frequency observation. Then you have to say that, oh, because the wave theory suggests that no matter what the frequency is, as long as the intensity is high enough, it can accumulate the energy and the electron can be emitted, right? Then the quantum theory states that only 1 electron can absorb 1 photon at a time. The photon must have the minimum energy. Therefore, the photon must have the minimum frequency, right, for the electron to be emitted. That's quantum theory. So if you need time to internalize this, go internalize this. These phrasings here are the phrasings for the essay, the explanation questions themselves. So go and internalize this. I can't do this with you. This is like me asking you to go memorize the solubility table. I'm not gonna do that. Okay? Okay? There's nothing not to get here, right? But if you want me to read this to you, it's like me reading a bedtime story to my kids. Right or not? Right? The Gruffalo is very hungry, right? He walks into the forest, right? Then he decides to go get a snack, eat some mushrooms, lay it on the floor, die. You know, the kind of thing, right? Yeah. I'm not gonna read it to you like a bedtime story. Go read it yourself. The paper now. What else is there to do? The paper. Yeah. That, I mean, I will continue this next time round. Right? This coming weekend. Right? I have to be sort of fair. I go through all the content on the weekday, then the weekend don't get anything, is it? Cannot be, right? Yeah. Okay, come paper. I gave you the order of the paper, yeah? What's the order of the paper? The order of the paper, I said. May 23 times on 1, paper 3, May 23 times on 2, paper 1, 2, 3. Okay? Yeah? Got the paper? Huh? I don't know also. Okay, hang on. Let me just do a quick one. I will just do a quick check. Time zone 1, paper 2. Any further questions here? Anyone? Hmm? What? 8A2. 8A2. 7? No need, right? 7? 7 okay, Fuyo, this one. Terminal speed, this one you all know how to do, Okay. Wow. What's this? 7B or 8B? 8B. 8B. Okay. What was the request? 8A2. Okay. Looks like I'm gonna have to do 8. Oh, goodness. What? Isn't this what I just went through? What nonsense? Okay, Ken, what's this? Okay. All right. Hey, wait, stop. Let me see your iPad. So while you're doing this paper, let me look at it. This now I want to see the first part. See the first part. I don't get it or not. How come you all don't draw pictures on You all don't draw pictures on I love drawing pictures on it. Okay, metal plate, photon, wavelength, force x8 nanometers. Electron comes out, Ke 1.8 eV. Correct or not? Correct or not? Okay. You worked out what's the work function. Work function, what's the work function? Come. How much? 0.86 what? Oh, 0.86 EV, 0.86 EV, Okay, 0.86 EV, right? Okay, so that means the photon must minimally have 0.86 EV of energy. Correct or not? So minimum, right, energy of photon is equal to 0.86 EV. What are you asking for? They're asking for what? Longest wavelength there. Wasn't it what I just said just now? I just did this like about 45 minutes ago, like quite early on in the lesson. They would ask you for what's the minimum frequency, right? Right, because we know E equals to HF, right? But HF is also equal to what? Yeah, HC over lambda. Over. You always say HC lambda. Your ACS boys are all the problem is there. HC over lambda. Right? So it makes sense. The minimum frequency is the longest wavelength. Huh? Then you HC over lambda equals to 0.86 EV converted to joules. You didn't convert to joules, you fool. Because you forget that in physics, right, all the physics equations are designed for SI units. SI units. If you don't convert to SI units, you are the SI. Okay? The stupid idiot. Alright, SI units. Okay, 8B part. 8B part. What again, Mingler? What? I cannot hear him. 8B part what? 8B part target. Wow. B part 1 Okay. So B part 1 has nothing to do with the first part. Okay. Alpha particles, initial KE of 5.9, directed at stationary lead, show that the distance of closest approach is this. Okay, now if let's say you are wondering, like, have we done this before? Have we done this before? The answer is yes, we have done this before. All right, where have we done this before? All right, you can go through the notes. You should be able to tell it's topic 12, right? It's here. We have done this before. Okay, there. Right, the kinetic energy is converted into EPE. Okay, so what's happening here? The alpha particles, we are ejecting it. I mean, you can consider it as a revision already lah. Right, we are ejecting it, and then we're letting it fly as close as possible to the nucleus, to a nucleus. The target nucleus in your question here is what? Is lead, right? Right, lead 207. Okay, you're trying to shoot the alpha particles at the lead 207. Okay, so the thing is, yes, you might be thinking, never mind lah, you don't get these 2 marks, it's fine, I move on. Okay, but you just have to make sure you got some safeguards. But once I go through this, hopefully you remember. So the key trigger of this question here, it says closest approach. Whenever you have to do closest approach, right, it's literally the alpha particle trying to reach the lead nucleus. Why can't it get any closer? I mean, why do we have to care about closest approach? Like, what's the purpose of this? Was that what? Estimate what? Estimate the nuclear size. We're trying to estimate how big is the nucleus. How do you tell how big is the nucleus? We fire alpha particles at it, right? When it gets very close, right, at the closest approach, right, because of repulsion, it will repel. So we got to understand that what is the KE here? What's the KE of the alpha particles right here, right next to the target nucleus? What's the KE there? 0. Why did it become 0? Why did it become 0? Because it got converted into electric potential energy, right? It's on the brink of U-turning. Okay, so to find this, you gotta have to kind of like imagine an alpha particle, right? I mean, honestly, the really what you're trying to do here is trying to learn, right? Not just get the calculations. You want the calculations, just look at the mark scheme, okay? So this alpha particle reaches a lead nucleus, right? I'm going to draw something a little bit bigger for the lead nucleus like this, right? Because it's chunky, right? Okay, so the lead PB 20782, okay? So the idea is that the alpha particles, right, had initial KE of 5.9 EV, 5.9, sorry, MeV, and then it goes to a closest approach and then it U-turns. So what is the KE there? 0, right? The KE there is 0. So now you have to do the KE convert to EPE equation, right? KE equals convert to EPE equation. So 5.9 MeV. Caleb, need to convert to joules or not? I wish you didn't tell me that. Because then, right, then why you convert for this one, you didn't convert for the other one? Okay, right. 5.9 MeV convert to joules, right? And it's equals to, so what's the equation for electric potential energy, EPE? You will have to do K QQ over R, no square is EPE, so no square, right? No square, okay? K QQ over R. Who's Q? Yeah. So Q, one of the Q's is for the lead nucleus, the other Q is for the alpha particles charge. Then some people say, but how do I know what's the charge of the alpha particle? Yeah, some people ask me, how do I know what's the charge of the alpha particle? Are you supposed to know the charge of the alpha particle? Yes. Hell yes. You're supposed to know what's the charge of the alpha particle. You need to know that the alpha particle is made up of 4, 2. That means it has 2 protons. And you need to know that the lead nucleus is made up of 82 protons. But what's the next common mistake that students make here? They forget that the 2 here and the 82 here, you still need to multiply to the charge of each elementary charge. That means the working looks like this, okay? All right, 5.9 convert to MeV, 5.9 times 10 to the power 6 times 1.6 times 10 to the power minus 19, right? That's the conversion to joules, right? Okay, equals to K. Okay, what's big Q? What's big Q? 82 times 1.6 times 10. I know this for a fact, right? Because like, oh no, in the past few batches, they forget to take this multiplied by this. They think it's 82, they realize that it's this term times that term. QQ lah. Yeah lah. Charge, yes. You think this is chem 82 times 2 How? You don't even take chem. Do you remember that you have to multiply these two or not? You did. You got this correct. You didn't get that one. Don't know what to do with you all no sometimes. Huh? Some of the worst thing is that it's not like you self-realize it was a mistake. Like. You asked me as though like there was something wrong and you didn't know why, you know. Correct or not? Well, you're highly inconsistent. Couldn't. Why? What is the more? Is this the reason why your score is like that? Why? Is it no? But I'm just very worried. That was the issue in the first place. So you got to check yourself many times. Okay? All right. Always self-evaluate. Okay. Anyway, cannot. Then anyway, the whole idea here is to just find R because R will be the closest distance that the alpha particle can reach. Okay. Trigger word is closest approach. You see the term closest approach is usually that one concept from topic 12. Really, it's legit just this same thing here always, right? From this part of the chapter here, like that. How do I move this thing? Yeah, there you go. Right. Yeah, the closest approach. Yeah, this is the closest approach method. Okay, Woo! Okay, can. Then anything else? 明日听明了。明了。Okay. Yeah, don't forget that one Hey, Dennis. Make sure I see a lot of people that they do this 82 plus 2, then they times 1.6. They only multiply this term only one time. Do you realize that you multiply 2 times that this number become very small? Because it's like 10 to the power minus 19 squared. The total value here become very small. Right? Yeah. Okay. And what's the purpose of this? The purpose is to try to get an estimate of how big the nucleus is. But is this a good estimate? No, it's not. It's an approximation because it actually tells you the size of the nucleus is like about that size, which is not quite right. But we know that it's going to be smaller than this. Right? Okay, good. So that's for B part 1. How about this one? Suggest why is there no deviations from this experiment. What was the R that you calculated? What was the R that you calculated here? How much is this? What's the value? 4 times 10 to the power of minus 14 meters. Okay? All right. 4 times 10 to the power minus 14 meters. So why is it that why there are no deviations from the Rutherford scattering? So you got to ask yourself right now, if you're not sure about this deviation of the Rutherford scattering, you can ask me for the videos, but very quickly, what was it? It was basically This one here, right? This was a predicted model, the dotted line. If the alpha particle has too much energy and it got too close, right, then there will be deviation. Deviation, like you see this on the dotted line here, and then this little balls here, those are the data, right? And the data deviated from the model. Y'all don't remember this, ah? Remember or don't remember? You remember. Those who don't remember, anyone who don't remember what this is about, ask me for the video. And I'm not punishing you for not remembering. I'm not saying like, wow, you don't remember, you're gonna die. No, I'm not gonna say that. Right? Don't remember, just text me and ask me this. Right? Can I have the recording for this? Right? Then yeah, okay, fine, no problem. Right? I got better things to do in life than to scold people for not remembering things. Right? I don't remember a lot of things myself. Right? Maybe 2 years, 3 years down the road, only I see you on the road, right? Sometimes I'll be standing there and I guarantee you I'll be standing there, I'll be wondering, shit, what's his name? But it happened to me so many times, right? It's like I know he comes on Monday, I know he comes to me, like I know he bought me this before, but then shit, what's his name? Yeah, names and my brain doesn't work. I don't know why. I can recognize the face, but I cannot recognize the name. Yeah. I don't know why also. It's a thing. So sometimes, right, you see me I on the streets, and you say hi to me, right? I get stuck, right? Then I would just be like, just help me out here. And then it's just like, hey, you remember me? I'm Caleb. Oh yeah, Caleb. Right. Yeah, this means, right? This will be the deviation. All right. And yeah. So would it get deviations? Why not? Like, how close must you be to get deviation from the Rutherford scattering? Which is deviation from the Rutherford scattering. Which is how much? Okay, so the order must be 10 to the power minus 15. Right? You can just quote the order can already. You don't have to quote 7. Because if you quote 7, what? Where? Oh, shit. Sorry. Yeah, I mean, yeah, okay, it's right there. So, what does this mean then? The closest approach is 10 to the power minus 14. But then the radius is 10 to the power minus 15. How far is the alpha particle's like closest distance? Like what? It was like 10 times this, right? It's like, the distance from here to here is like 10 to the power minus 14 distance. Right? That was that far away. Right? Okay. The deviation is caused by what? The deviation from the scattering is caused by what? What is it caused by? It's caused by the strong force. And what's the range of the strong force? Which is what? 10 to the power minus 15, right? If you write that down, your 2 marks is in the bag, solid for you, right? Because that's exactly what it is, right? Right? The alpha particle will not deviate from the scattering, right? Because it's too far away. Strong force cannot take effect on the alpha particle, right? Range of strong force is 10 to the power minus 15. Good. All right. Yeah, that's pretty much it. Okay. I don't know why Kirti told me that I have a capacitor question. This one here. This one here. I'm supposed to go through this. I don't understand why. I think nobody asked. I think I just answer her lah. Yeah, cause like then that one is just her problem. Yesterday's class. Okay, come. 23 questions. Yeah, this one here. No questions. No questions. I move on.
Always
Careless. Careless means you couldn't care less. Come on. Any questions here? All right, this one here. This thing here. What? I went through this one before with you guys. Okay, can. But anything here? Or haven't do yet? Haven't do yet, go and do. Don't forget about this section A. Really legit. Right? This is where your marks, don't lose it lah. You know what I'm saying? Right? I'm also pushing the year 5s to do it because the year 5s are the year 5s has a new structure paper. It's very strange. There's paper 1 MCQ, and then there's paper 1 uncertainty questions. Yeah. So I have to keep on pushing them because they're so frazzled about like the waves, they're so frazzled about the angular momentum questions and all that. Yeah, they have to do that shit. Right? Then they forget about this topic. So I have to keep pushing them to do this one here. Anyway, we good? So calling once, calling twice, right? So, but here's the thing, imaging got do or not? Got do or not? Astro got do or not? Astro got do, right? Yeah, like Astro do finish already, right? This one. Imaging got do or not? Have you done it yet? Done already. Okay. If you haven't done it, it's okay. Because I'm not going to go through it today. I'm not going to go through it this week. When am I going to go through? Next week, after your school end, after you don't have to wear school uniform anymore already. Next week. Okay? So it's likely next Monday, right? Next Monday, I teach a class, right? Then you'll just stay back for imaging. Then on Wednesday is Astro though. But then, next week, the timing change already. Next week, you still have to go back school or not? Where you stay? Okay lah. Then yeah, hopefully the train is done by then, right? How you gonna go home today? Huh?
I use downtown.
Downtown you go cashew and then you walk back home okay. Wow, shag man. Yeah, I'm stuck in no man's land. I'm at Clementi, right in the middle there. Yeah, I look out the window, I can see the depot where the damaged train went into. Oh, shit. That's like living in JB. Okay. All right. So just take note of that. Okay. Yeah. Oh, good luck to your year fives. They have to do this shit. They have to do relativity. It's part of their core syllabus. Yeah, they do time dilation. Yeah, all these. You see, oh, gross. Gross. Huh? No. That does imaging for IB. Yeah. All the other schools, even the international schools, all do astrophysics. You know why? Because it's the easiest to teach. Right? How do you teach astrophysics? Go and study lor. You just need to memorize what? What's the difference between a meteorite and meteoroid? That one I can teach you, man. You go memorize it. I give you the notes lah. Right or not? That's the easiest to teach. That's why they all do astrophysics. Imaging is damn freaking hard actually. That's why I always thought that maybe there's a difficulty multiplier to it, no? Like if you do imaging, right? Let's say you get like 10 marks, right? They give you a multiplier 1.3, then you actually get 13 marks. Right? I don't know. Maybe they moderate based on the option they take. I don't know. I hope they do. Anyway, so no calls for paper 3. Now it's just the next one. Time zone 2, paper 1. A lot. Both. Time zone 2, paper 1. Question 1 and question 1. Okay. Tell me. I'm gonna type it out in chat. Come.
Question 6.
So nervous. 6. 11. What else?
5.
5. 22. Text me your score. No, text me your score. No. Text me your score. Text me. You tell me for what? Text me. Please keep it in. Oh my god, I only got like another 45 minutes only. Thank you for text. 23 lah, May 23, right?
It's 23.
Shit, I'm doing May 2023, bro. Okay. You texted me 22. You score? 24?
I realized my mistake.
No, that's not the point. Wait, 24 is not a good indicator. That's not good. You're supposed to be like at 28 now already. What happened? Don't tell me you don't know. Can you realize your mistakes earlier on or not? Like,
At least I realized it.
can you realize it before you do the shade on the OTA scan? Score. Text me your score. This one lah. 23 time zone 2 paper 1. Walao, I keep asking you all to do, then what?
More questions.
Move my head. What? Move my what? Can I move my what? What do you want me to move? Okay, fine. I don't know what you want me to move. I move my head lah. What?
More questions.
Some more questions from this paper?
Yeah.
Then say lah.
16.
16,
18.
11, 16.
28.
28.
27.
Okay, I tell you this. Those that got 60% for your prelim plus minus 5%, okay? Your safe zone. Those who didn't, better start bucking up and do more. I know. I aim you already, you know. The others that got like 57, 58%, right? I mean, after I see some of the papers, I kind of like sort of know, firstly, the marking is a scam. The marking is a scam. Paper 3 marking is a scam. Right? Then you got scammed. You have to do more practice, Ken. Don't okay me. Go and get it done. Goodness. 33. Another one. 27. I can go and buy Toto already. What? 36.
Because
This paper sucks. What's the score? 30. 30 okay lah. Better than 25.
usually when I saw that's about the song, I just don't know.
You just don't know. Oh, jialat. That sounds bad. Okay. Alright. Question 5 first. Let's look at 5. 3 don't need, 3 don't need, 3 you know how to figure this out, right? You show me A and D, there's you choose either A or D, I'm gonna like you know, yeah. 5, 5, 5. Okay, 5. What's this? Fuyo. What's this? It doesn't slide. Doesn't slide. So if it doesn't slide means what? Isn't this mg sine theta? Right? Hang on, let me just draw the arrow a bit carefully first. Mg sine theta, right? Doesn't slide. Mg sine theta. Then the friction is how much? The friction is like that. The friction is yes, as well. Can. I do 5 already. I go back 4. So does not slide, right? Then does it mean that mg sine theta equals to mu n? Equal, right? Am I missing any force along the slope? Don't have, right? These are the two forces along the slope, right? Then the frictional force. Oh, they ask you for frictional force. Then proportional sine theta lah. So this answer lah.
Yeah, just should.
No, what do you put down first?
Yeah, put the correct.
You put the correct answer, but you don't know why.
I don't know why it can't be C.
You don't know why it can't be C.
But like normal force is proportional to
The normal force is proportional to cosine theta because when you resolve the weight, right? Then there's a normal contact force and the weight is mg cosine theta, right? The n is equals to mg cosine theta. The n force is proportional to cosine theta.
but I thought the F equals to mu n, so it's possible.
So you wait.
That's why
Wait. I didn't consider that. So mu n is it? So mu mg cosine theta. So why is the friction not proportional? Wait. Then you should say this. You should start with this because now I'm confused. Right? Isn't friction proportional to cosine theta? You have to think about how cosine theta changes, how it changes as you increase theta. Cosine 0 is 1. So if you increase theta, 1. So if you increase theta, if you increase theta, then cosine theta the value theta, then cosine theta the value, right, becomes less. And as long as it doesn't slide down, the frictional force actually increases with sine theta, because as theta increases, sine theta increases. It's a very strange thing to say.
it's proportional to negative.
It's proportional to negative cosine theta. That's hella weird though. But yeah, I can see where the confusion is. Yeah, I can see where the confusion is. I mean, I would just choose D because of what I just did. But because I went to dig in a bit further now, so I would think that as theta increases, cosine theta actually decreases, right? But as theta increases, the frictional force actually increases. So while this is increasing, cosine theta is actually decreasing. So it's not directly proportional to cosine theta, right? Because f increases, cosine theta decreases. Wow, that's actually quite scary though. Like I didn't even consider that. Yeah, right. So as theta increases, right, f increases as well, right? Sine theta increases, but then cosine theta decreases. Yeah, wow. What a yeah, so this one here will decrease, or this one here increases. So they're not proportional. Hmm, so scary. Okay, then yeah, that means the normal contact force decreases with increasing theta. Yeah, as theta increases, right, the normal contact force by the ramp is actually getting less and less and less. Yeah, okay. So that's question five. Question five, surprisingly, is a little bit more complicated than I thought it was. But yeah, okay. Question four, let's look at four. Okay. Object is traveling with velocity of 5 meters per second. Then it accelerates to 15 meters per second in the same direction. In the same direction. So it's traveling with constant velocity. Right? So are we right to say that it's traveling with constant velocity first? Right? Constant velocity at first. Constant velocity. Then it accelerates to 15. To 15. Okay. But the problem with these graphs here, they're all acceleration time graphs. Right? They're all acceleration time graphs. So what does that mean? It's zero. Okay? So your job is to understand that when your object accelerates to 15 meters per second, right? Right, to 15 meters per second, you have to look for one of the graphs where the triangle is equal to 15 meters per second, like the equal to 15, the area. What? Oh, sorry, yeah. So from 5 to 15, so the area is equal to 10 meters per second. So you need to look for an area that gives you 10 meters per second. Dia, this area here, isn't it 10? 10 meters per second. Because it's the acceleration time graph. Isabel, okay? Isabel. Okay, yeah. The others cannot because this graph here, this one is a triangle here like this. This area is way too big, right? The area there is also way too big. Yeah, the area under acceleration time graph gives you the gain in velocity. Area under AT graph, right? Change in velocity. Okay, there we go. So that's for number 4. Okay, the next one being 6. 6 okay, 6 here like this. Right, it says compress, placed between two stationary masses, release so the masses move in opposite directions. What's the KE of M and KE of M, right? Small mass and big mass. So, how should you approach this question in the first place? Hmm? But what's the underlying concept that you need to consider here? Come on, tell me what are your considerations while you're doing this one. Imagine you're doing this now, Caleb. What are the underlying principles that you need to consider here? Yeah, lah. Momentum, right? What's the initial momentum here? 0. Then when the two masses starts flying off from each other, right? So when the two masses start flying away from each other, what's the total momentum here? Also 0, right? Also 0. So am I right to say that M1 V1 M2 V2, right? M2 V2 M1 V1 equals to M2 V2. I mean, yeah, it's equals to the negative lah. Okay, not? I mean, that's the first step. That's the first step, right? First step here. Okay, now What if you went down the wrong path and you decide to think of force instead, right? Because you might be thinking, oh, I might be thinking, okay, so exert the same amount of force on both sides, correct? The spring will exert the same. You want to use what to find? Like let's say you consider force. What will you? Which path will you be going down here like this? If you consider force, right? Force on each side. Then what's the next thing? Force. And then what? Some of you might even think of acceleration, right? Force divided by this mass gives you acceleration. Then once you get acceleration, then you see your endpoint. You still need to get ke. Then you might be thinking, so how do I get from acceleration to ke? Huh? Then you start doing suvet, right? Then after that you start realizing, oh shit, I don't have the time, I don't have the distance traveled, I can't do it. Then what do? Backtrack. Just go backtrack, right? Don't try to go there already. You realize that you need more information, like you need distance, you need time. Then you backtrack and then consider another, right? Consider another method. So then you should consider momentum. Okay, then you should consider momentum. Now, how do you relate momentum to KE? How do you relate momentum to KE? Is there a relationship between what's the relationship? Yeah, KE is equals to P squared over 2m. K equals to P squared over 2m, right? P squared over 2m. There you go. So that means that you can go and put in the P squared over 2m of small m and the P squared over 2m of big M, and both of them have the same momentum. Right, so Ke of small m over Ke of big M is equals to P squared over 2m, right? And P squared over 2 big M, like that. Okay? Oh, I mean, they did say big mass is twice that of small m lah. They did say that up there. So what happens here then? Well, everything cancels off. So it's basically 1 over m over 1 over 2m. Can math? Can math, right? Yeah, so what's that? Isn't that 2? That's just 2. That's 2. That's 2 there. 2. 2. C is your answer. Okay? Okay, 6 done. 11, come. 11. Okay, 11. Got do? 11? You put D, you got right or wrong? It's wrong. Okay, let me see your working. Let me see your working. Let me see your working. Okay, I mean, you at least you got draw the close end and open end. Okay, so you draw close end, open end, right? Okay, close end, open end. Denise. Details, details, details. Third harmonic. How many waves are inside the pipe? Third harmonic. 3 what? 3 quarters, 3 quarters. And 3 quarters. That looks way more than 3 quarters. But that's where you made a mistake. So you already drew it out already, but you drew it wrongly because you went to draw. I don't know what you draw there. Then you can tell me now fifth harmonic. Then you draw that one for what? Draw 3 quarters. 1 3 quarters. This is 3 quarters of a wave. Like that. Fish. Like that. Then this one, the third harmonic is 150 hertz. Okay, 150 hertz like this. Oh. Hey, you're not wrong actually. You're not wrong.
Is it like the second or
It's an n equals to 3. That means it's really 3 quarters. That means the L is equals to 3 quarter wavelength. Yeah. Because IB has, because they've asked for one end open, one end closed, right? The actual IB question, they asked for the second harmonic. And the second harmonic is this one. Yeah. So what they want? They want this all. As of May 23, the latest version, right? IB recognizes that when you have one end closed, one end open, when they say third harmonic, right, it's the 3/4 wavelength. Okay? This is the standard we are following now because this is the latest standard. If they decide to change, right, we can go and fight with them. Yeah, we can go and fight with them after that. Right? Some of you to say, I don't care, I want to take back my paper and I want to review it or something like that. They have to pay money for it, but if they spot something like this, they can go and fight for it. Then everyone's marks must change. Yeah. Okay, so hopefully they wake up their bloody idea, right? So as of now, we established that IB standard, when they say one end closed, one end open, third harmonic, is 3/4 of a wavelength. We take it as that, right? This is the evidence. Okay, this is the standard. So that's what they want. Okay, so anyway, what's the first harmonic then? What's the first harmonic frequency? 50 hertz. 50 hertz, huh? Isn't that the answer? That's the answer, right? Okay. Wait, so 50, 150. What's the next one? 250. Right? 50, 150, 250. Isn't it? Right? The harmonics will be 50 hertz. Then 150 hertz. Then the next one is 250 hertz. First harmonic, third harmonic, fifth harmonic. Fifth harmonic times 5. 250. Next one is what? Yes. 350 hertz. That's why D is not an answer. Right? Because some students will also think, hey, but 50, right? Then the next few, how come 300 cannot? Right? This is the reason why. Because this is first harmonic, third harmonic, fifth harmonic, seventh harmonic. Okay? Good. Next one, come. Hey, Caleb, one more time. You have all this knowledge in your head, you're not putting into practice, so you have to practice. Do you practice enough or not before the prelims? So occupied with which subject? Math. Your math okay? Can you load balance now? Can I ask you to put some attention? For you, right, I tell you this. I got a feeling that it's just practice only. It's the type of weird questions that they ask. Because every time I ask questions in class, right, you can always answer me on. You can always tell me the concept of it. So what you need to do is you need to put your concepts into application. So practice. Can? Okay, All right. 11 done. Next one is what? 16. Let's do it. 16. Wow, damn gross What the hell? Wow, Kirchhoff in 1 minute. What's this, man? Kirchhoff. Is it no choice? I think no choice, no. Can meh? Cannot lah. Cannot lah. Anyway, I won't risk it. I'll just do Kirchhoff. So my job is to find I1, is it?
Yeah.
Then after that, loop, one loop here. What's the loop? E equals to I1x plus equal resistance. Sorry, I1R, is it? Okay, I1R plus I1 plus I2R. Okay, then 2E is equals to I1 plus I2R. Is that right? Okay, then like that, then I see this already. I see this, I sub it inside here. Then that's it, right? So the EMF equals to what? You got do or not? You got do Kirchhoff or not?
Yeah.
You messed up the Kirchhoff. Some people, they get stuck here. They should use Kirchhoff. Then they get stuck here. Then they get stuck here already, right? Then all the time wasted, right? Just commit, right? Just commit. If you really cannot make it, backtrack. Link here, can. So E is equals to I1R plus 2E, right? 2E, 2 da di da di. So basically I1 is what? I1 is equals to, I1 is negative. Negative E over R. Negative, right? Yeah, negative, but negative sign don't care, right? It just means that I chose the wrong current at first. That means I chose negative value. So that means in reality, it's actually pointing this way. Yeah, like that. Okay, lah, but anyway, I got the magnitude already, it doesn't matter, right? So C is my answer. Can? Okay, good. 16 done. 18. 18. 18. What's the direction of magnetic force acting on the sphere? Wait, who's asking for 18? Dave. Okay, you tell me which topic is this? What's that? Topic 5, but which part of 5? You see this negative charge? What's the sides? What? You don't sabo people not A levels. Everyone do well, everyone get the 7. This one not A levels. A levels is you sabo everyone already, right? Then you can get the A because everyone else is shit. She remembers.
What?
Huh? What nonsense? This is magnetic field. This is electric charge. This is 5.3. The negative charge is falling, so the current is pointing up. D. You fool. Oh. Current point up, field point to the from north to south. Right? So the force is in. So this charge will start to will deflect into the page. So this is your answer.
Confused magnetic field.
You confuse magnetic field and magnetic what?
Force. I'm confused.
You think they will be so dumb to go and create this whole diagram for you just to say that the magnetic field points to the right? This one is careless. Careless cannot cure one. Right? Careless is cannot cure one. Yeah. 19 or not? 22. What's this? Does the count rate 45, is it? It got background this one. Wow, tricky. Yeah, I didn't see it. Who asked for 22? I just went through this on Sunday. Never pay attention. Never watch it. Never watch it. Only right, Saturday, Sunday, I finish up nuclear, right?
You did 5.